So far we have learnt that in physics we come across two kinds of quantities. These are vectors and scalars. We learnt that vectors have both magnitude and direction, while scalars have only magnitude. We also learnt that vectors are equal if they have the same magnitude and if they are in the same direction. Then we learnt how to add vectors and subtract vectors. We also learnt the law of parallelogram vector addition, and with the help of that we can find the resultant of two vectors. Remember that resultant is nothing but the sum of two vectors, and the law of parallelogram helps us in finding the magnitude and the direction of the resultant. In this lecture, we shall talk of the multiplication of vectors. Multiplication is in two stages. One, multiplication of a vector by a scalar, and two, multiplication of a vector by a vector. So, let us take the multiplication of a vector by a scalar first. If we multiply a vector A by a scalar k, then the product is a vector whose magnitude is the absolute value of k times the magnitude of vector A. You remember, when I say absolute value, I mean both negative and positive have been reduced to positive. That is, if k is minus 3, its absolute value is 3. If k is plus 3, even then its absolute value is 3. So, when I multiply a vector A by a scalar k, then the magnitude of the vector is increased k times. That means, the magnitude of the new vector is k times the magnitude of the vector A, and the direction of the new vector remains unchanged if k is positive. That is, if I multiply a vector by a positive quantity, its magnitude increases, but the direction remains the same. If k is negative, the direction of the new vector is opposite to its original direction. For example, vector 3 times vector A has thrice the magnitude of vector A, but it is in the same direction as vector A. But vector minus 3 A is in a direction opposite to vector A, although its magnitude is thrice that of vector A. Now, we come to product of by another vector. Here again there are two types. One is the scalar product of vectors. As the name suggests, the scalar product of two vectors is a scalar. The scalar product of two vectors A and B is written as vector A dot vector B. It is also called the dot product, because we have put a dot between vector A and vector B to indicate the scalar product. So, the scalar product is A dot B, vector A dot vector B. This is also called the dot product. Let us see how we do it. We have two vectors here, vectors A and vector B. So, how do we multiply them? We join first of all vector A and vector B and find the angle between them. Suppose this angle is theta, then the product A dot B is equal to A B cosine theta, where A is the magnitude of vector A, B is the magnitude of vector B, and theta is the angle between these two vectors. Remember that vector A dot vector B is always equal to A B cosine theta. Theta is the angle between them, and the product is a scalar quantity. You can see that there is no vector A B cos theta. Notice that B cos theta is actually the projection of vector B on vector A. You see, we have drawn a perpendicular from the tip of vector B onto vector A, and the projection is given by B cos theta, and the product becomes A B cos theta. So, therefore, the dot product of vector A with vector B is the product of the magnitude of vector A with the projection of vector B on A. The result is A B cos theta. A well known example of the dot product is the work done when a force F produces a displacement d in an object. The work done is written as W is equal to vector F dot vector d. If the force and displacement are in the same direction, then the work done is W equal to F d, as you have learnt many times in your classroom. So, work done then when force and displacement are parallel to each other, then the work done is F d, where F is the magnitude of the force, d is the magnitude of the displacement. Here you can see that you can drop a perpendicular onto the force if F and d are not collinear. If F and d are not in the straight line, they have an angle theta between them, then you can find a component of displacement along the force, and this component as written here is d cos theta, and therefore, the product of F dot d, that is F vector dot d vector, is equal to F d cos theta, which is equal to the work done. So, when force F and displacement d are at an angle theta make an angle theta with each other, then the work done is F d cos theta. Notice that it does not matter whether we take the outer or the inner angle between the two vectors. We have shown here the inner angle is theta, the outer angle is pi minus theta, because cos of theta is equal to cos pi minus theta. Therefore, it does not matter whether you take inner angle is theta, the outer angle is 2 pi minus theta, and therefore, it does not matter whether you take the inner angle or the outer angle, because cos theta is equal to cos 2 pi minus theta. Since the dot product is a scalar, it is commutative. That means, vector A dot vector B is equal to vector B dot vector A, and both are equal to A B cos theta. So, the order does not matter. You can have A dot B or B dot A. The product is always the same, A B cos theta, and it is also distributive. Again, the order does not matter. A dot B plus C is A dot B plus A dot C. So, it is distributive, that you can, that vector A dot vector B plus C is vector A dot vector B plus vector A dot vector C. Other category of vector products is what is known as the vector product or cross product. Here we are multiplying two vectors, and we shall see that the result would again be a vector. The vector product of vectors A and vector B is written as vector C, where vector C is equal to vector A cross vector B, and since there is a cross between A and B, this is also known as a cross product. So, whether it is vector product or cross product, it is the same thing. It gives a vector C which is equal to vector A cross vector B. Notice that C is also a vector. So, the result of a vector product is another vector. Now, suppose we have two vectors A and B, and the angle between them is theta as usual. We can draw a plane omega which contains both these vectors. As shown here, we have vector A and vector B, there is angle between them and they are in the same plane omega. What is the product? The vector product of these vectors has magnitude A B sin theta, and its direction is perpendicular to both the vectors, that is perpendicular to the plane omega. Let me repeat, vector product of A and B is a vector which is perpendicular to both A and B, and its magnitude is A B sin theta, where theta is the angle between them. How do you find this direction? Whether when I say it is perpendicular to the plane, whether it is the perpendicular is upwards or downwards. This we find with the help of what is known as the right hand screw rule. We imagine a screw which is right handed, that is, if we rotate it like this, it goes down. If we rotate it like this, then it goes up. So, you can imagine that there is a screw placed at the point where two vectors A and B are joined. Now, if we want to find out the direction of the vector C, which is the vector product of vector A and B, then you imagine rotating this screw from A to B. So, you imagine the arrows show this kind of rotation. So, you rotate from A to B, and what do you find? As you rotate from A to B, you find the screw goes down. That means, the vector product of vector A and B is perpendicular to both A and B and is in the downward direction, as shown here. There is another way also to find the direction of the product vector. In this case, we use what is known as the right hand thumb rule. If we are going to multiply vector B, let us say in this case vector B with vector A, that is, we are going to get vector B cross vector A, then we curl the fingers of our hand from B to A, and the direction of the thumb gives the direction of the product vector. Here I show you the rotation. Here we rotate from curl our fingers so that they rotate from B to A, and then the thumb gives the direction of the product vector. If we have to take A cross B, then we will have to curl our fingers from A to B, and then you will see the thumb comes down. Therefore, A cross B in this case would be downwards perpendicular to both A and B, and B cross A is upwards perpendicular to both A and B. So, these are two rules, the right hand thumb rule or the right hand screw rule, which can help you get the direction of the product vector. Please, it is important if you remember this, otherwise you will not be able to get the direction of the vector product. So, let me repeat therefore the one of these, at least the screw type, the right hand screw rule. You rotate, if you are going to find the product A cross B, then you rotate from A to B. Imagine a right hand screw rule, imagine a right hand screw, rotate from A to B and see the direction in which the screw advances. When we rotate from A to B, the screw advances in the downward direction. Therefore, the vector product A cross B is equal to C, which is downwards. Now, for example, the cross product of vector x along the x axis with vector y along the y axis gives vector z along the z axis. You can see y. Here I have shown x and y, and you can see if I rotate a screw, or imagine rotating a screw from x to y, you can see from the motion of my hand that the screw will go up. Therefore, the vector product of vector x and vector y is a vector in the z direction, positive z direction. You can also see that if I reverse the order, that is, if I multiply vector y by vector x, then what happens? Then I have to do this way from y to x, and you can see that the screw, imaginary screw, advances downwards, and therefore, the vector product of y with x, y cross x is downwards in the minus z direction, as I will show you here. This is in the positive z direction and this is in the negative z direction. So, the cross product of vector x and vector y is along the positive z direction, and the cross product of vector y with vector x is in the negative z direction. And you can see that in this case and in every case in fact x cross y is equal to minus y cross x. Now, what does follow from this? That if we have a plane, again let us take a plane and let us have two vectors a and b in the plane, and as we have seen before, the vector product is downwards shown as vector c. Now, suppose I change vectors a and b, rotate them in the same plane. As I have shown here, the angle between them now is changed. It was phi, now it becomes theta, or if it was theta earlier, it becomes phi. The angle has changed, the vector magnitudes have not changed, but they can be changed. Vector magnitude have not changed, and the cross product remains in the same direction, that is plane to the perpendicular to the plane in the downward direction. That is, if I have two vectors in the same plane, whether I rotate them, whether I change their magnitude, as long as they remain in the same plane, their vector product is perpendicular to the plane in the downward direction, if I am taking the vector product a cross b. Its magnitude can change depending upon the angle between them, depending upon the magnitudes of the two vectors. The magnitude of the product can change, but the direction will not, as long as the vectors remain in the same plane. Now, as I have been saying, cross product of two vectors is a very important concept in physics. The cross product is perpendicular to both the vectors of which the product is being taken. Its magnitude is equal to the magnitude of one vector multiplied by the magnitude of the other vector into sine of the angle between them. In this case, it is important that you take smaller angle between the two vectors. You remember, in the case of dot product, I showed you the smaller angle and the larger angle, which is 2 pi minus theta, and in that case it did not matter, because cos theta is equal to cos 2 pi minus theta. In this case it matters, because sin theta is not equal to sin 2 pi minus theta. So, therefore, be careful when you take cross product a b sin theta, theta is the smaller angle between, or the inner angle between the two vectors. Some important formulae where cross product is employed in physics are angular momentum, which is the product of position vector r and the momentum vector p. Angular momentum vector L is equal to vector r crossed vector p. Torque is equal to the cross product of the position vector r and the force applied, force vector which is applied. Lorentz force is F equal to E v cross b, where E is the charge, v is the velocity of charged particle, and b is the magnetic field in which the charged particle is moving. In the next lecture, we shall take up resolution of vectors. We shall see how a vector can be resolved into components along the axes of the frame of reference.